Okay, so good morning, everyone. Thank you for coming to the second part of the training session for the Women in Data Science Datathon Maastricht. So now you already know how to create your notebooks for the competition. Many of you already managed to make a submission and to learn the scores of your pipeline. And yesterday, Shan already introduced you to, to the data pipeline and to exploratory data analysis, right? So now you know a lot about data exploration. So I will continue with the other steps of the pipeline and also tell you a little bit more about how data exploration can help you to improve your model. So now you create a baseline. We will try to improve that baseline by knowing more of all the steps involved in this process, right? So let's start by introducing the main machine learning pipeline, which is conformed by the data processing pipeline and the classification at the end. We started in data exploration, right? So here, with these steps, you will find out how the different features behave. So you will be able to explore their mean values, their variance, if there are unique, how many unique values are there, and also how many missing values, right? And even some type of correlation of the features with the target. So after that, using this knowledge, you may be able to fill the missing values of the data. Usually we can do something like filling those missing values with a mean value if it is the case for continuous features. But also you can use more sophisticated methods like classification methods that may help you to improve the ways in which you are imputing the missing values, right? So besides that, you can also remove columns that are not informative, for example, that have only one value in the whole column, right? This can perfectly happen in real world data sets. So besides that, you can also remove redundant features because if you already have one column that represents some type of features, you don't need another column representing the same information, right? So this may be harmful for classifiers because you will have this information duplicated. And if the feature is not sufficiently discriminative to be able to provide a good classification, then you are duplicating bad features, right? So after these steps where you should be able to, to clean your data, to impute missing values, then we go to feature transformation. There, you will be able, for example, to aggregate features. You will be able to scale features, for instance, for the use of distance-based classifiers. So in the case of distance-based classifiers, if there are features that have a, a higher interval, so for example, they go from 1 to 100 compared to other features that go from 0 to 1 interval, then those features that are in a larger interval will probably determine your classification. So what we want to do is to give equal weight to all the features. So we know that there are no features that are probably not discriminative and can influence the result of our classification. But of course, this step is only possible for the case of numerical continuous features. So besides that, we can do some type of encoding, right? In the case of categorical features, because the classifiers need a way to handle those categorical features. So either categorical or binary features. And we have to choose a proper way to encode those features. And once we have those features encoded, then we want to do some type of feature selection, right? Because there may be features that are not informative or even harmful for the classifiers. So then we can either choose to select the best features or to discard the worst features, right? There are many approaches to do that. For example, there are criteria based on filter methods such as the chi-square, as a type of forward feature selection, and there is also backward elimination. But many classifiers that use in their criteria also the feature importance are able to provide those importances. So you can, for example, in the case of the random forest, check what are the most important or relevant and informative features for this classifier. So with this feature selection, you can do many things. You can either use one method, you can combine some methods for feature selection and find the commonalities between the set of selected features, right? So once we selected our features, we go to the data modeling and classification pipeline. So now we have already our features computed. We know that they are clean, we know that they are encoded in a way that classifiers can handle them. We know that we already tried to select the most relevant features for our pipeline. So now the next steps will be to find good classifiers, right? There are many options for this. So we can start with simple ones, such as logistic regression, such as linear methods, for example, the linear discriminant, and also some nonlinear methods that are still not complex, but introduces some nonlinearities, which can help with data that is difficult, right? That is complex, that has a difficult distribution. And besides that, there are also even more complex methods that model more nonlinear data, such as decision trees, such as k-nearest neighbors, and other types of trees and other types of boosting methods. So here we can also choose to combine the classifiers, right? Usually, classifier combination improves classification results. And besides that, we can also try to optimize the parameters of the individual classifiers by doing some type of grid search. This usually takes time. So if you are going to use this type of approach, you have to do it fast because it takes time to find the best set of parameters. So once you choose your classifier or your classifier combination, then you have to try to see what are the results of this pipeline, right? What type of results you can obtain with the individual classifiers or with the combination. And for that, you are going to see also how we can partition our data in a way that we can use a part for training and the other part for testing, or either use a cross-validation where in a number of times you will divide your set in different folds, and this type of strategy will help you to use different training sets and different test sets and find a better compromise for the accuracy of the method. So you will be able to understand better the accuracy of your method. So we will see more about this. And let's start with some of the data exploration parts. So for example, you saw yesterday many ways to do data exploration. And here I show an example of the weight and height features that we have in our data. So if you look at the distribution of the weight and height for male and females, we can see that they are different, right? We have different, they look like normal distributions, right? Something like that, not yet normal, but something like that. But what we can see is that the mean values, right? The mean of these distributions is different for males and females. So we can use this knowledge, for example, in our pipeline to impute missing values. So in the case of continuous features, in the case of these numerical features, we may want to impute by using the mean of the features, right? But we know that the mean is different for males and females. So we can use this knowledge to provide a better estimate of the value that we want to impute. So instead of using the whole mean, what we do is to separate the way that we impute these values for male and female. In the case of both height and weight, what we do is that if we check that the gender is female, we know what type of mean we want to use. And if we know that it's male, then we know that we want to use the male mean, right? And this is the type of decisions and the type of insights that data exploration can help, right? So besides that, we can find in many data sets that some features or columns have way too many missing values to be used for our classifier. So if we are going to impute those, we know that with imputation, you usually introduce errors, right? But if almost the whole column is represented by missing values, then you will introduce probably many errors, and we want to avoid that. So what we do usually is that we discard those columns that are really full of missing values, and we don't want to use them for a classifier. So we choose some type of threshold. For example, in this case, I chose those that have more than 80% of missing values, and we drop the full column, right? So then we will try to impute the remaining ones, the ones that have less than 80% missing values. So besides that, we can have rows after we already drop all those columns. We can still have rows that have too many missing values for us. So we don't want to use those rows. And we can also choose here a threshold, for example, dropping those rows with more than 50% missing values. We have to be very careful in these steps because we don't want to lose too much training data, right? So we have to find a compromise. We have to find this threshold carefully. But of course, we don't want to use samples that have probably almost all the values missing, right? Okay, so we do that. We drop columns and rows of our training set, but not from the test set. So the test set that you should use to make the submission, you cannot drop samples there. You can drop columns because you have to process this in the same way you process the training features, right? If you drop columns in the training set, you have to drop the same columns in the test set that you will use for the submission file. And also, there is also a possibility of processing this test set independently. And if you find that there are also columns with too many missing values, you can drop those and then also go to the training set and drop them, because we need consistency between these two sets, right? But you cannot drop samples from your submission sets. So now we know that, so that you can either choose to drop the columns after you join the two sets, or you drop in the train and do the same for the test, or you drop in the test and also do the same for the training. So here it was somehow comfortable for me to use the arrays of the categorical columns and binary columns names to handle now the remaining missing values. So I did that, but it is also possible to use this file that they give you also with the data, where all these variables are identified. So now we are going to fill the missing values. So there are two ways if you want to fill those missing values with the general methods, right? For example, if you want to fill for the binary columns, you can do that by filling with a fixed number. So a fixed code that you know that is different from the actual values. In the case of binary, we have zeros and ones, and here we will fill with a code that is 10. And then the classifier will realize that this is not telling anything, so we cannot do much in the case that the sample comes with this value for the missing value. However, there is a catch here. In the case of medical data, there are hints, for example, for some features, that if the feature is not there, this can represent knowledge as well, because it may mean that the person is either healthy, at least that the doctor thinks that it's healthy, or is too sick to measure the value, right? So it can provide information. The fact that the value is missing can also provide information in some cases, at least for medical data. So yeah, there are some catches with this. So you can do it this way, but you can also do it with imputers. So you can use either a simple imputer, an iterative imputer, or a more complex classifier. So in the case of the simple imputer, what you have is almost the same code that I'm doing here, but you can send the parameters stating what type of strategy you will use for filling the value, such as a constant or a mean or a median or the value that repeats the most. So there are different ways to do that. And in the case of the categorical features, here what we are doing is that we are selecting the feature that repeats the most in the column. So in the case of classifiers for imputation, what you do is that, for example, in the nearest neighbor case, you select your neighbors, right, and see how this feature behaves for your neighbors. So this is a more granular strategy than if you use the whole sets for imputation, and also if you use some features like we saw in the first example, like the gender or the ethnicity. So to impute based on the values of these subsets of others that have your same gender or your same ethnicity. So there are different levels of granularity to fill these missing values. And of course, if you use these more complex classifiers like the k-nearest neighbor, it seems that you may probably have a better missing value imputation, right? But of course, these methods also take more time to run, so you have to be careful with the time with this. So it's a compromise now in this type of Datathon. So for the numerical features, we try now to detect them, and then based on this list, we also fill, for example, with the mean. Here I'm using the gender and the ethnicity groups. So we have a better estimate of those means. And now we print how many missing values remain in our data. And in this case, it's 0 because we already fill now the different categories, or even the binary, the categorical features, and the numerical features. So for example, now, we already filled the missing values. Now, what do we do with our data? So one interesting thing that you can do for these data sets is that you can create new features from the ones that are already there. For example, why should we do that? Because you may be able to create new informative features from the information that is already there. So those features can probably add more discriminative information. So what I do here is that for the case of the body mass index and for the case of the blood pressure, you find in your data the values, the actual values for blood pressure measurements and for body mass index measurements. But we know that they are grouped into categories that are the ones that are more clinically relevant, right? So doctors, what they look is that if you are underweight, or if you are overweight, or if your blood pressure is low, or if it is high in any of the 3 relevant categories. So what we can do in this case is to create a new column, a new feature with these categories that we create from our data. So after we do this, we find that from columns that probably have have like hundreds or thousands of different unique values, now we can have only 4 unique values in the case of body mass index, or 4 or 5 unique values in the case of blood pressure categories. How can this help? So besides of being clinically relevant, the classifier can learn better how to provide a category for samples with this, because if you have more unique values, then it is possible to overfit, to overtrain, which are concepts that are heavily studied in this type of pipeline and really affect classification performance. So you have to really, if your interval is really large, you have many unique categories, then you have to go really deep, for example, in the case of random forest, and this will create overfitting for your data. So this is one example, but there are also many other examples. You can either combine features by concatenating them. You can either divide features, because this can have some clinically relevant information, but you can also use clinically relevant information to impute missing values. So for example, you may know that if you have one column with missing value, this column corresponds maybe to the division of 2 other columns. Then you can use that division to fill the missing values. But of course, you need to really know about these issues, right? You need to know more about clinical things. But there are really many things that can be done in this data for data imputation using clinical knowledge, but also you can create many new features using clinical knowledge. So these are tips to process your data before going more for the machine learning, artificial intelligence part of this pipeline. So after we created new features, now we have our data set complete. So we want to encode the categorical features, because we saw that classifiers cannot handle, some of the classifiers cannot handle the data as it was, as raw data. So we need to provide either a one-hot encoding, like Shang explained yesterday, or a different type of encoding, named, for example, ordinal encoding, which instead of doing the one-hot thing, what they do is that they provide values for the category. For example, if there are 5 categories, they may provide the values from 1 to 5. So this type of approach is usually more effective for classification trees, right? For random forests, for all those classifiers that have some type of tree-based behavior. Because if this feature vector grows too much, which is the case of using one-hot encoding, this causes issues for this classifier. So this may be, you have to try, but probably in this case, if you are going to use trees, the ordinal encoding will be better than a one-hot encoding. So after we encode our data, I choose to separate again the training and test sets here. At some moment, you have to do it at the end, because you have to train with the train set and then test with the submission set. So what we do now is that once they are separated, we do some type of correlation removal. So we saw why we need to do that. We don't want correlated features. And you can do that easily with this code. So by analyzing the correlation matrix and then dropping those columns that have a high correlation with others. Also, you have to choose your threshold carefully. And here I use this threshold. So that is really a high correlation. So now we can see that we have these 2 values for the number of samples for one class and for the other class. So usually in these clinical settings, the class of healthy persons, in this case of non-diabetic persons, is really higher. So we have much more samples for this class than for the class of diabetic persons, right? because this is what happens in the real world, right? In reality. So what we want to do is to balance this set, to balance this training set, because if we send this as it is to the classifiers, usually this creates problems because the classifiers will learn better from the class that is better represented in the training set. So we want that our classifier learns in the same way for the two classes, because diabetic patients really need to have also a good classification. We don't want to miss a patient that has diabetes by classifying it as non-diabetic. We don't want that. So we always need to handle the imbalance in our data in some way, right? So what we can do is handle it in the data pipeline or handle this directly in the classifiers. Some classifiers allow this. For example, the random forest that you saw in the notebook from Sean yesterday, it has a parameter that says that you should give higher weight, right, to the class that has a lower amount of samples. So this is for the random forest, but not all classifiers can do that, can handle this directly by setting the weights inside the classifier. So what we can do is to upsample our minority class since the data pipeline. And what we can do here is to replicate exactly, duplicate our minority class as we are doing here, or we can use more advanced methods like the smooth method. So I also have the code here for that. It takes longer to run, but it is probably a better way to handle this problem. So for example, here, instead of duplicating the samples, what the method is doing is that it finds some type of linearities between samples, between random samples, and then fills in the linear function between two random samples a new sample there. So it generates these new samples in a way that they are not exactly the same that the ones that were there in the training data, but they are close and there are linear relations of the original data. So in this way, we are not duplicating data, and duplicating data may be a problem for some classifiers as well. But I choose the simple method. So we see that we have now our data with a correct number of objects or samples for each of the classes. So now we are going to scale the numerical features, the continuous features. Why we do that? Because we saw that if we have one feature that has a large interval, it will determine the classification results, and we want to avoid that. We want that only the discriminative features are the ones that determine the classification results. So we will give equal weight to all the continuous features because we still don't know which are the ones that are more discriminative. So we do that here, and we use this scalar function. And with this, now we already have our continuous features scale. So we know that there is no problem for distance-based classifiers, right? So here I show a simple visualization of our data. And I did this because you can see that the two classes are really overlapped, and this is not good for classifiers. So this tells you that this problem is a difficult one, and you have to be really careful with what you do because, for example, a linear method will not be able to separate those classes. So we need something more complex, right? We need some type of more complex classifier. So let me see. Yeah. So for example, this is an example that I created to show you also how these methods that I mentioned about the nearest neighbor can impute the missing values. So I wanted to show you here, for instance, that the less granular approaches will just provide the mean of all those for imputing the missing values. So in the case of the more smart weights, what the method does is that it uses the values of the nearest objects to impute the missing value of the point. So let me see if I can continue here with other visualizations for you. So yes, so I told you that this data was really difficult to classify because it was highly overlapped. So this one is also overlap, but we can see that it's less overlap than what we have for our training data, right? But ideally, we will want to have this, right? So that each class is really completely disjoint from the other class. That we can, for example, draw a line here and we can perfectly separate the two classes with a line, right? So in the case of more complex feature distributions, probably a line would not be enough. So a linear classifier would not be enough. So we may need a nonlinear classifier, like some type of polynomial function. But what we have here really requires more advanced classifiers. So either decision trees, either nearest neighbor classifier, or even some deep learning methods, right? Because it really requires to unravel many nonlinearities that are in the data, and you will see that in the results. Because if the data is really perfectly separated as this one, results are usually very good. It's usually more than 95% accuracy, but if not, your accuracy would be usually lower than 85, right? So now we will talk about feature selection. So we have our data ready, but we want to know which features to send to the classifier. So we already saw that random forests can do that. Random forests already use a criterion to search for the correct class, and this criterion provides a measure of how relevant are the features. So we can rank those features by the random forest. And we can decide to select, for example, the top features that the random forest detects as most relevant, the top 10, the top 20, top 30. But we have to be careful, because if we look at the results of another feature selector, like in this case, this method, the lasso method, then you will see that the type of features that the method finds as more relevant are not exactly the same as the ones the random forest finds. So this tells us that probably it may be good to combine results of both feature selectors, or that we may use one feature selector and then the classifier that selects a different type of features with the selection of the other method, because this may somehow avoid problems like overfitting, right? So we want more diversity inside our classifier's behavior. So this is also a possibility to use the best lasso features according to the methods and use them in the random forest, for example. Or you can combine results from both. So what I did here is that I combined the chi-square feature selector with lasso and random forest and selected the join set. So now we have our set of features. We have classifiers that we want to train with those features to provide the classification results for our submission test set, right? So we need to know what is the accuracy to have an idea of how to improve the method. Once we find the baseline accuracy, we will try to improve this accuracy using the same protocol that we use to find the accuracy. So we have to fix this protocol, and if our method improves this protocol will show us that it is improving because the precision, the accuracy of the classification results will be higher, right? If you are improving, but be careful because they will be higher for a test data that you will select here. But that does not always mean that they will be higher for the submission. So you have to be careful with that. So to do that, we need the model validation approaches. So we have all our training set that is here, what we call all data. And we have to divide this into training data for the classifier and test data to find how is the behavior of the classifier. So we can do this by dividing into 80% for training and 20% for testing, for example, but you can choose another type of values there, like 50-50. And you can also do what we call cross-validation, which is also a line of code you will see, and you send your whole training data there. And the method of cross-validation takes care of dividing your data. For example, if it is a 5-fold cross-validation, it divides the data 5 times, and each time it divides this data into 5 folds. And it uses, for example, 4 folds for training and 1 for testing. What this gives you is diversity in the results, so you know how sensitive your classifier will be to different sets of training and testing, right? And you find the mean of the results for each of these splits. So this strategy is good to find as best as possible how your classifier behaves, right? To really find the accuracy. But if your final goal is to improve the classifier, I think you can perfectly use this strategy of dividing only once into training and test, always with the same percent for each set. And if possible, also set the parameter of the random seed that you will find for these methods with the same numbers. So then you know that you always have the same training data and the same test data. So if you find an improvement, it was with the same data. So this method is also very good. It's also very good to understand the accuracy of your classifier. You can choose either of the two to improve your final classification result. So we have the strategy, and now we will see the classifiers, right? For the classifiers, you can start, for example, with a simple decision tree. And you divide your data in the beginning, and you fit your decision tree on your training set, and then you can compute the accuracy for your test sets. And you can also compute, as I mentioned, the cross-validation accuracies, right? So here I show some visualization of this decision tree, and it is really very auto-explainable because you really see what the method is doing easily. It's similar to rule-based methods. So you see that here the first feature that it uses to split the data into potential classes is the glucose level, right? It makes sense because we know that diabetes is really closely related to glucose levels. So here it is already establishing classifications, right? If the level is this, it gives you one class. If the level is this other, it gives you another class, and it keeps going depending on how the different features behave on the different cuts of this tree. Then you will reach one leaf, and this leaf will give you a classification for each sample. So after it was trained, you can send unseen samples that the method did not use for training, and it will be capable of giving this unseen sample a classification. So you send it here, and then it goes through the tree, and it will find a given leaf that will provide its classification. So this is one simple example, but probably you will need more complex classifiers for your problem. So for that, I also added here many possibilities, from most simple ones to more nonlinear and complex ones, and even having different type of behavior. So some of them are more distance-based, some of them are more based on statistics, on probabilities, and what I choose for my pipeline were the ones based on trees because they provide the best results. So you have to set for them the different parameters, the number of estimators for the trees, because in this case, they behave not only like one tree, but they use several trees and then use some type of mean, some type of aggregated result from all those trees to provide the final classification. So we know that usually these approaches provide the best results in these competitions, right? This combined with deep learning. So we will try to use them. So I use this one and random forest also based on decision trees, but also a distance-based classifier based on the nearest neighbors. I use also my parameter for the neighbors. I compute their individual accuracies to understand how they behave for this problem. And finally, I'm going to combine all those results in a voting classifier. So what this voting classifier does is that it considers all the individual classifications and then use some type of majority vote to provide the final classification result. For this, we have to set the different weights. If we trust more some of the classifiers, we give them higher weight if we think that they will provide higher accuracies. Then for others, we give lower weights, but usually it is good to combine classifiers that provide diversity. So classifiers that are different in nature usually provides better results in this type of ensemble voting methods or other ensemble methods. So there are more. I chose this, but you can find much more methods that behave like ensemble methods. All of them based on different criteria for the combination, for aggregating results of the individual models. So usually this voting and ensemble methods in general take time to run. So this is something to consider, and yeah, be careful, because if you want to test them, you know that it will take some more time than individual classifiers. So with this, I can compute the accuracies of all my individual methods, but also the accuracy of my ensemble classifier, right? And once I compute those accuracies, I want to compute the labels that we will assign to our submission test sets. So what we will do here is that we will use now the whole training set, not the division into training and testing, but we have to join all those again and train our classifier with this whole set, because we don't want to lose any sample. We want to have the most information that we can get. So we will use now all the samples for training our final classifier. And with this classifier, we will assign then the classes to our sample submission file. And with this that you already saw in your notebooks, we will have our submission file, and we will find how we score in the ranking on the competition. So this is mainly what we have to do if we have to classify our submission samples, but there are other possibilities. So now we are using the same data preparation pipeline for our classifiers, but it is also possible to use different types of processing for the data for different classifiers. You can do that at least in Python by using the pipelines. So when you add to your final voting scheme each of the individual classifiers, you can also add, for example, what type of operations, as I show here, on the data you will do for the individual classifier. In this case, for example, if I'm going to use the nearest neighbor, I also want to do some type of preprocessing for my numerical continuous features before the classifier, for example. So I want to do this like I show here by a method that selects the given columns that I want to use. So that is, for example, if you want to use your clinical knowledge and you say these columns related to the Apache values, columns related to glucose and to hemoglobin values are useful because I know that they are the most informative, then you can select them directly, and this method is doing that. It selects directly the columns that you want, and you have, of course, to implement the method fit transform. It's not like any standard method, but it really requires that you provide fit transform functionalities and other feature selectors that are already there in sklearn modules. They do that directly, like the chi-square, like the forward feature selector. They implement those functionalities directly, but if you want to program this from scratch, you have to create those yourself. So in this case, I want to select given columns, and I want to pass those columns directly to my nearest neighbor classifier. So I do that here, and I create a pipeline that first selects the features and then have the classifier on those features. So when we add our models for our pipeline, then we either add individual classifiers that use the data as it was processed before, or add classifiers with another type of preprocessing for the data. This is also possible if you want to do something that is really useful for only one classifier but not for others. For example, if you know that this operation will benefit a given classifier and not the others, then you can do that. And this is usually what happens in practice, right? That a given preprocessing is good for one and not always for others. So this is also another option that we have to create our classifiers pipeline. And yeah, you finally find your accuracies and have your submission file ready to submit. So I think I can stop here. So if you have any questions, I will try to make this notebook available to all of you. So you can see the different type of commented code that I have there for different type of options, either for feature selection, for classification, or for missing value imputation, or for upsampling the minority set. So do we have questions?